Get this to a little better spot. So the first one, you kind of see the graph up there. Not looking for a perfect graph because nobody's perfect, just a good representation. With inverse functions, the inputs and the outputs have what relationship? Switcheroo, right? Yeah, they just like literally switched. And then the composition of two inverses, either way, if f and g are inverses, if you do f of g of x or g of f of x, either way, you should just get an x. You should just go back to the input if you compose two inverses. Questions, comments about that first page there? All right. So then the other page is all the limit stuff. Do a little zoom here. Guess that sort of works. So that last one ends up being 1/128, or 1/2 to the 7. Same thing. Yeah, so please do check those out. I'm thinking that letter M might have been a challenge for you, that limit of a composite. Maybe, I don't know, maybe it wasn't too hard for you, maybe you did fine. But let's do talk if you have any questions on any of those. Yeah, go ahead.
So on H, if you're approaching 2 from the positive side, wouldn't that be -1?
I don't know, let's find out. Let's see. Hopefully there's an error. If there is, let's fix it. So for H, as you approach 2, -1. I agree. Yep. Let's try this. Sorry. I don't know why it jumped on me there. Yeah, -1, I agree with that. Thanks for asking. Okay, anything else? You guys do okay with that? Okay. Just give you a minute to ponder. Think it over. A really important part of our culture is that you feel free. I hope you will eventually feel free to just ask. If something's not making sense. One focus here and then you're learning.
So
Question.
For letter M,
Yes.
So you find the limit as -2 from the negative side for g of x. And
Yep.
then the y value of that becomes the limit for h of x.
Exactly right. And this one, you explained that really well, and I think it's pretty straightforward when you think about it like that. There are some that get a little more complicated than that. We'll get to those later on. But yeah, you said that quite well. Carter.
I just skipped a step, so I was just wondering what I might have skipped for M.
You skipped a step?
I think.
I mean, those steps I showed were just sort of like FYI. I don't think that you really have to show those for this one. I wouldn't be terribly upset if you didn't.
Okay.
What do you think? Like, I'm not sure. Did you get the right answer?
Yeah, I got the right answer, but I just didn't really get this.
So, like the way that Nate put it there is you start off by evaluating the limit at the inside function. Right, so the inside function is g. And so we ask ourselves, all right, as we approach -2 from the left for g, we see that that's 2, right? -2 from the left, so we're talking about right here. That makes sense? So -2 from the left, we're approaching a value of 2. So then that becomes the new limit evaluation point for the outside function. And so the outside function was defined as this. And so that's why I wrote this, limit as x approaches 2 of that outside function. And then that one was a little bit, like to finish it was a little more straightforward because since sine of pi over 3x is nice and continuous, we can just do that direct substitution and it works. There's no need to do any extra fancy stuff like factoring or whatever. So I would defer back to what Nate said. I think he explained that pretty well. So as long as you are at least thinking those steps, I think you're doing pretty good.
Okay, I see where I went wrong, but it was the same answer.
Okay. Okay, fair enough. Anybody else? Okay, good deal. So, yeah, tomorrow there will not be a warm-up. Tomorrow there will be review quiz 1 when you guys come to class. Okay. Flip ahead. Let's do some continuity. So this first little piece here is for you guys to consider continuity of those graphs. So please look those over, and it says, which of the following graphs is or are continuous at x equals 3? I just want you to indicate what you're thinking there as far as which one or which ones are continuous at 3, at x equals 3. And this is just a visual exercise. We have not defined continuity at all. Say again?
Was this one not, we're not supposed to do that?
Well, no, we did that one. I had that one up there.
Oh, I just didn't.
Oh, it's not limit as x goes to infinity.
Oh, that's.
You treated it like it was
Okay.
got as x goes to infinity.
Would you just plug 4 in that instance?
If you plug 4 in, you're actually going to get a 0 in the denominator. So you're going to have to factor and cancel.
Okay.
Your answer should be 1 over 128 for your final answer. Okay, how many of these graphs do you guys think are continuous? Which one? The cubic looking, yeah, it's probably a cubic, right? Lower right. So this one down here, lower right, is continuous. And the other 3 are definitely not continuous. Only that lower right one is continuous. And I want to go a little bit deeper here and talk about the different types of discontinuities that we have on those other ones. And these terms that I'm going to talk to you about are terms that you're going to want to know. Okay? And I think they're fairly self-evident as far as the names of them. So upper left, clearly a discontinuity. Does anyone want to venture a guess based on the way the graph looks? What would we call that discontinuity? No guesses? Yeah. Oh, even nicely done. Way to turn that into an adjective. Yeah, let's call it what it is. This is an asymptotic discontinuity, or you could just say it's a vertical asymptote. Okay, so that is a term you would want to know. Like you'd want to be able to associate that kind of a graph with an asymptotic or an asymptote discontinuity. All right, let's do the lower left one. Clearly a point of discontinuity there at 3. Anyone want to venture a guess as to what we would call that point of discontinuity? It's very descriptive.
2 lines.
No? It's 2 different graphs, right? Clearly a piecewise graph. I think we could maybe come to that conclusion. But yeah, what would you call that? What is the graph doing right there at 3?
Disconnected.
It's disconnected, yeah. And if we think of the graph as almost like a personality or a person,
Bipolar.
the graph is, no. Yeah, the person, I guess I did say the word personality. Physically think. What is the graph doing? It's physically jumping. This is called a jump discontinuity. Jump discontinuity. So you'd want to know that. So if you ever saw a graph or an equation that had something like that, and then I said, hey, there's a discontinuity, what would you call it? You'd want to call it a jump discontinuity, because literally the value at 3, the value of the y's, is jumping from -1 to 5. It's jumping. The upper right one, a lot of people will call that a hole or a gap, which is a pretty good description. This is the only one that seems a little bit strange as far as the name goes. Upper right is called a removable discontinuity. You'll see this in your discontinuity. There we go. If you were to look at your textbook, you'd see that term as well. College Board chooses to use that for themselves too. It's called removable. I guess you could say because the other ones are not removable. This is the only one that is. Think of it like this. This is why it's called removable. Couldn't we take this clearly piecewise defined point, and if we just redefined it up there, wouldn't this then become a continuous function? So if you can remove the discontinuity just by redefining a piece of the function, it's called removable. You do not have that luxury with the asymptote or the jump. You can't just say, hey, let's throw another point in the right spot and we have a continuous function. It's not going to work. And so that's why that one is called removable and the other ones are not. Okay, so I want to hear from you guys here. What do you think needs to be true for a function to be continuous at x equals 3? What are some of the elements that you can think of? What's one of them, Hunter?
Can't be a hole at the point.
No hole. Okay, so I would say no hole. Doesn't that mean that, I'll just call this f of x. Could I just say like f of 3 exists? Like in other words, you can't just have like a hole there, right? You need to have like an actual output at that place. What do you think, Luke? What else?
The right hand and left hand limit have to be equal to the function at point.
Yeah, so the right limit has to equal the left limit. Is that more or less what you said?
Yeah, and has to equal the f of 3.
Has to equal f of 3? Okay. Wow, that's actually pretty good. What do you think, Cole?
Taking an asymptote at F3.
Absolutely. And if you think about it, if there's not an asymptote, that's actually a pretty nice description of saying, hey, f of 3 has to exist, right? Because if there's an asymptote right there, f of 3 does not exist. And so by saying that, you're right, there's no asymptote. So if we eliminate that, now we have a possibility of continuity. Yeah. Okay. So everything, yeah, go ahead, Nate.
So, I mean, we said, like, no hole, f of 3 exists, and then the right limit and the left limit has to be the same, but, like, with the removable discontinuity, f of 3 exists, but it's still not.
And that's why I said what Luke mentioned was actually pretty darn good, because you bring up a really good point. Because if we didn't say what Luke said, then the issue you're bringing up with that upper right-hand graph would be an issue, be a problem. But he said, hey, the left-handed limit has to equal the right-handed limit, and they both have to equal the value of the function, which is kind of what you were addressing. You're saying, hey, wait a minute, you could have this and this, but not that. We have a problem. And he actually kind of addressed that already. That's why I was pretty impressed. I'm impressed that you noticed that too, because a lot of people just think of it as the limits, but you got to include the value of the function too. Yeah. Okay, this is all really good. You guys are catching on quite well. Contributions have been really positive. So let's do this. Let's take all these ideas right here, and we're gonna flip over to the next page, and we're gonna write this a little more formally. And I hope that you'll be able to see how everything that has just been mentioned is a pretty nice descriptor of what we really need to think about with these. So here it is. I'm just going to write it right on this nice continuous graph. The formal definition of continuity, let's just do this. This will be better. Okay, so here it is. The limit as x approaches, I've got a 5 right here. I'll just use 5. Limit as x approaches 5 from the left of my function has to equal f of 5, and that has to equal the right-hand behavior as well. So the right-hand behavior, the left-hand behavior have to equal each other, and they both have to equal the actual y value of the function at that point. Okay, and that's like sort of taking what Luke, Nate, everybody else said there and writing it formally. And this right here, this is what we're going to use. We're going to use this. We'll use this a lot. So anyways, and this can be written in different orders. So I will often write it like this. So if I wrote, I'll just be real general here. If I wrote like limit as x approaches c from the left equals limit as x approaches c from the right equals f of c. I've changed the order a little bit, but I'm saying the same thing, right? So left-hand behavior equals right-hand behavior equals the y value of the function. That's no different than what I just wrote up above. Same thing. Highly encourage you to be flexible with that, but you will probably see me personally most often writing it this way. But it's okay to be flexible too. Okay. So you're going to hear me say this a bunch, so I'll start off by saying it now. If I'm going to, like, anytime a teacher or really anybody says always, I think you should probably take note. I'm going to say this, feeling pretty confident. If you are ever asked about continuity in any aspect, always start off with limits like this, okay? If you're ever asked about some aspect of continuity, start off with this limit statement about continuity, and it's probably not going to lead you in the wrong direction, okay? So if you would, take a peek at our first question with these continuity type questions. Number 1 says, is f of x, that piecewise defined graph there, function, is that continuous at x equals 2? If f of x is not continuous, we're going to classify the discontinuity as removable, a jump, or a vertical asymptote discontinuity. So, if you're asked about continuity and you don't start off with that lovely limit statement that I just showed you, you're starting off in the wrong direction. So start off with that limit statement and you should be in good shape. So you guys feel like you can run with this at all? A little bit? Yes? No? Maybe? I'll give you a couple minutes. Okay. Good. I know you always feel like you're sticking your neck out there if you say you're doing good, right? Any questions on anything? I don't think so. Okay. All right. Well, let me try to show you what I think would be some really nice steps here. And again, let me just emphasize for you: if you were asked something about continuity, you need to start off with that nice limit statement about continuity. So here's where I would start with this one. I would say the limit as x approaches 2 from the left of f of x possibly equals the limit as x approaches 2 from the right of f of x, which possibly equals f of 2. So I put those little question marks up there because I don't know if that statement is true yet. If you don't have the question marks, it's probably not the end of the world. It's really the right thing to do. But we're just kind of testing this out to see if this is true or false. So again, I would encourage you, if you made some progress on this one, please look at your paper. And if you don't have a statement like that written down, you got some work to do, right? You need to transition over to where you're starting off with something like this. Okay, so the left piece, is the left piece the parabola or the line?
The line.
It's the line, right, based on the domain there. And so if you wanted to, you could do this. You could put the specific pieces in there. So you could have this, and the parabola would go here, and f of 2, that would be the line again. So f of 2 would be -9. Something like that. So then we actually test these limits out. So the limit as x approaches 2 from the left of -4x minus 1, that's -9. Maybe equals, then when you try the 2 out in that middle limit, you get 3 times 4 is 12. 12 minus 7 is 5. Okay, so now we finally arrive at this and say, well, -9 really doesn't equal 5. We have a little problem there. So conclusion number 1, is this function continuous at 2? No. So not continuous at x equals 2. And did anybody take it one step further and decide what kind of discontinuity it is? What do y'all think? Just shout it out. Jump, yes. Because the left-hand behavior is heading towards -9 and the right-hand behavior is heading towards 5, you're going to get one of these guys, right? And so you could be specific here and put it's a jump discontinuity. And if we had lots of time, we would actually graph this thing out and come up with this lovely graph. You're welcome to do that, but we don't have time to spend
Would it be all right
at
to
this
solve
point.
it that way? Because that's kind of how I solved it. I sketched a quick graph.
So, yeah, so let's talk about that. So if that's all you put, we have a problem.
Right.
Because graphs can lie to you sometimes, right? You're like,
Right.
well, I looked at a graph and it told me this. We can find plenty of graphs that will just lie to you. If you had that limit statement, and then I can see there you've got your graph, and that looks like actually a pretty nice graph right there. If that graph was just kind of part of your thinking, but it wasn't like basically, hey, look at my graph.
That's all my work, right?
Yeah, that would be a problem if that was all your work. But if you've got the limit statement to go along with, the
Okay.
numbers to kind of support, that's actually a really nice answer if you did that.
Okay.
Yeah, but we want to avoid saying, hey, look at my graph, figure it out. So I'm sure you can understand why. Good question. Anybody else with a question? All right. Very good. So then, I don't remember what's next. I'm kind of excited. What is it? Oh, yes. Yeah. So let's do this one. Number 2, sort of a similar question. And again, let me reinforce, if some question says, hey, blah, 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 something about continuity, figure out something about continuity, you need to start off with that limit statement regarding continuity. So see if you can do that for number 2. And then number 3 will be a little bit different. Continuity, or is something continuous, you need to start off with that limit statement regarding continuity. So I would start off with this. The limit as x approaches 1 from the left of g of x needs to equal, or possibly is equal to, the limit as x approaches 1 from the right of the same thing. And then those two things would have to equal g of 1. So hopefully at some point you realize that g of 1 doesn't exist, right? G of 1, if you try to plug a 1 in for x, you get a 0 in the denominator, and regardless of what that looks like on the graph, there is no output for that. So I would put dne over there. And then maybe you handle your limits. Maybe do you guys all do the factoring and canceling routine? So when you do that, you get 2, and that equals 2. But of course, that does not equal dne. And so, no, g of x is not continuous. So we could say g of x has a discontinuity, I'll put blank discontinuity at x equals 1. Did anybody determine what kind of discontinuity it is? Why don't you shout it out? Removable. It's a removable, which is a hole. I agree, but we're going to call it a removable. And I want to see if you can see the graph through the limits. Can you guys see over here how essentially this, what I'm putting in the red box here, doesn't this mean that the left and right hand behaviors are the same? Yeah. From the left and right, we're both heading towards 2, but as soon as you get to 2, there's a hole, right? Just that one little point, no y value. It doesn't exist. And so that's a description of this. Left-hand behavior, same as right-hand behavior, but right there, where they would try to meet, there's a hole. That's the dne part. Okay. Questions, concerns? You guys are doing a good job working through these. Are you all comfortable with this concept of like me showing you things and you trying it? And you fall on your face, you succeed, or somewhere in between, and then we try to recover, pick up the pieces as needed, move forward. Is that okay with you? We'll do this a lot, and it'll get even more group intensive as we move forward. All right, I got one last thing to do here, and I want to work this one with you guys. It's the last one. Yep. So this is number 3, and this one is worded differently than numbers 1 and 2. Numbers 1 and 2 said, hey, is this function continuous, yes or no? And number 3 deals with continuity again here, but please notice that it's different in the sense that it doesn't ask you if something is continuous or not. It says, if g of x equals that, find the value of a so that g of x is continuous. So in other words, a is some constant, like it might be a 5 or a 3/19 or a 2/27 or a 13.6. We don't know what it's going to be, but we want to find the a value so that this actually is a continuous function. And so we're going to use our good limit notation, right, because I'm asking you about continuity. So let's start off like this. Hopefully this will be a good reinforcement for our last one. I'm going to say limit as x approaches -2 from the left. What's the left piece? Is the left piece the cubic or the line? It's the line. So I'll just put -3/4 x minus 2 has to equal the limit as x approaches negative 2 from the right of the cubic, ax cubed plus 4, bless you, and that has to equal g of negative 2. So notice, I was asked about finding something or other in regarding continuity, so I started off with my nice limit statement with continuity. And I'm just going to evaluate my two limits. And I think direct substitution is going to work on both. So for the first one, if I plug in the negative 2, what do I get?
Negative 1/2.
3/2 minus 2, I think negative 1/2. Right? You get positive 3/2 minus 2. Yeah, negative 1/2. Equals, if I plug a negative 2 in for the second limits evaluation, what do I get there? There should be an A, right? Because we're plugging the negative 2 in for the x, because it's when x approaches negative 2. Negative 8a plus 4, yeah. Now that last piece with the g of negative 2, I don't need to write that again. Which piece actually contains g of negative 2? Yeah, the cubic, right? The top one. So I could rewrite. I mean, if I really wanted to, I could write this again. But do you see how there's really no point in doing that? So I'll leave that part off. And then what are we left with? A lovely equation, which for you guys would be pretty easy to solve, right? We just subtract the 4 over. And then divide by negative 8. So we get positive 9/16 is A. So, in order for that cubic and that line to perfectly match up at negative 2, apparently the A has to be 9/16. And again, if you are really curious, and if you are, I support you on this, and you wanted to actually take these and graph them out and see, yes, indeed, they do actually meet right there. It'd be a fun activity. But as you can see, we've got like 2 minutes left, so I don't know that we have the time to actually do that. No. Anyway, tomorrow, very first thing will be review quiz 1. Remember, go back and look through your notes packet and see what actually could be on that and make sure you're good to go. And we'll start off tomorrow with that. And is there, I can't remember. Let me look at this and make sure. I don't think we have any intro activities or anything else. No.
There you go.
Hey, can I share with you one more thing since I still have like 1 minute here? I'm going to go back in time just a little bit. So you have your review quiz 1 tomorrow, but I also want to think about on Thursday you have your quiz on limits, first quiz on limits. If you've been keeping up with your WebAssign, the couple of assignments, and you're thinking, I could use a little more practice, I just wanted to show you that that's in here. So notice after the limits, there's this section that's called Practice for Concept 1. And this is just open practice. You can either do it or not. It's totally up to you. But if you want to do a retry on quiz 1, you're going to have to do this. So it's up to you how you want to handle it. You can do it on the front end, back end, or not at all, whatever you choose to do. But there's a lot of them. You can see, 29 questions you could practice on. I have not posted the answers yet, but I've got a little sticky on my computer to post the answers. So I will do that. Review quizzes are not retakeable. And my thinking on that is, you know what's going to be on them. Like there is no mystery. But the quiz ones, like I'm leaving a little mystery to that, and it's new, so I feel like a couple of retries is warranted. Okay. So, yeah.
Can we redo just one per semester?
On the quizzes? No, you can redo. Remember, you can do up to 2 retries, but you can do retries on all of them. I mean, hopefully you don't need to, but if you do, you do. It's okay. So, all right, hey, have a great day. See you guys. What's up, Cole?
So there's like 19 quizzes in a semester, you get 18 total retries.
Say one more time.